Welcome back, my little physicists. Today, we're going to talk about a whole bunch of stuff. The reason for that, oh no, why is all my pens all goofed? All right. The reason we're going to talk about a whole bunch of stuff is because you folks picked a unit that has a whole bunch of just random topics shoved together in it. Not so much that they're actually random; they kind of do go together, but they're not like the most cohesive thing in the world. They're not like Newton's three laws, right? There's not like three of them that very obviously go together. But we'll make do. So, what we're going to talk about today are the universal law of gravitation. We're going to talk about gravity, which is kind of the same thing. We're going to talk about these things called vector fields, and the difference, or maybe the lack of difference, between what's called inertial mass and gravitational mass. I hope I can impress upon you the distinction the AP test wants me to make about these things, and then kind of bring it back together. And I don't know. Bring it back together and show you that there's not a whole lot of difference. Like, the difference is one of semantics, right? Anyway, we'll see when we get there. Okay, I'm not gonna beat around the bush and try and describe it to you before I describe it to you. So let's dive into it. Okay, let's talk about vector fields and vectors first. So a vector field is a very handy thing that we have in physics. And what a vector field does is a vector field gives the strength of something as a function of position and sometimes time. What I mean by the strength of something, the something we're talking about here is probably a force. The strength of the gravitational force, the strength of a magnet, the magnetic force, the strength of the wind. You could draw a vector field for wind. Things like that. It's how strong something is. The strength of a current in a river. All of these things could be represented with a vector field. And as far as physics and the forces we're going to be talking about, the fields we're really going to examine today are in particular the gravitational field, but we'll kind of dabble with the electrical field. I'll kind of hand wave it for you and go, yep, it exists. But the way you want to think about a vector field is what it's showing you is how strong something would be if there were something there, if there was something there. So if we have a gravitational field, here's the Earth, as you can tell by these beautiful continents and these swirly clouds. Oh no, here comes a hurricane. The gravitational field is something that's all around us. It's basically the force, right? You feel the force. I'm in tune with nature, right? But can you see it? I mean, you know what I mean? How do you know gravity's there? It's just because everything sticks to the ground, right? Everything sits on top of something else because it's being pulled down. But what's pulling it down? Um, Actually, I heard recently this really wonderful theory for what gravity really is. A student that I know, a high school student, asked me, how do we know that gravity isn't an army of invisible dwarves pulling down on us with infinity invisible ropes? And I was just dumbfounded. I had no idea that that was even possible. And I don't know that I have a good explanation for why it's not an army of invisible dwarves with invisible ropes pulling down on us. Maybe it is, you know? Maybe that's a good metaphor for gravity. But a vector field is an invisible thing. It's kind of a math thing where it's some lines that we draw somewhere to represent how strong something is. the way vector field lines work, like these yellow arrows around the Earth, is the more tightly packed together they are, the stronger the thing in question is. So let me give you an example here. If we have a smaller, bluer Earth, let me draw this using some tools instead of freehand. There we go. A smaller, bluer Earth. Let's make 2 smaller, bluer Earths. Let's clone that. Okay. If I draw some vector field lines, we don't want blue. We want green. If I draw some vector field lines to represent, here's how strong the force of gravity is on this small blue planet. Okay. The arrows are pointing at what direction the invisible would-be force is going to be pulling on us if we're there. Notice there's not actually anything out here floating in space by this tiny blue planet, right? There's not like a little teacup here. There's not actually a little teacup floating out in space. But if there were, we all kind of agree that gravity would probably pull on it. I don't have a reason to think that there's like a hole in gravity here where it doesn't pull on it. So these vector field lines tell me what direction the force would apply onto this hypothetical teacup if it were out there. If I draw something like this, and then we'll put maybe some more. Let's put some like this, and let's put some like this. Okay. So this small blue planet has 1, 2, 3, 4 field lines. This small blue planet has, starting at the top one, 1, 2, 3, 4, 5, 6, 7, 8. Because it has double the number of field lines, we're saying that this field is twice as strong as this field. And that's pretty much what vector fields are. They're invisible made-up lines to represent a force that we think would probably apply there if there was an object there. And that's pretty much what you got to know about it. Let's take a look at some forces that are often described with field lines, and then we will, we'll talk about them. This lesson feels a little wishy-washy. Again, these are some topics that I don't necessarily know are super important, but we'll talk about them. So there are actually 4 forces in the whole universe that physicists know of, that we think, right? Like, of course, this is like as far as we know. People used to think the Earth was flat, and if women could read, they were witches. So here's the 4 forces that we know as best as we can, right? There's gravity. That's the force that a massive thing like Mars pulls on other things with mass, and they pull on each other because I don't know why, because they do. So there's kind of like the mass force. Because heavy things exist, they attract other heavy things. Maybe it's love. Maybe love is the invisible attractor. There's also the electromagnetic force. So if these are 2 magnets, 2 very beautifully drawn magnets, there's some invisible field lines, right? They kind of go like this. If you've ever seen magnets, like if you put iron filings near your magnets, they make field lines like this. And if you put some sprinkle of iron dust around them, the dust will form around these cool rings. So there's the electromagnetic force. Electricity and magnetism are actually the same thing. You'll learn about that when you get to college, hopefully. If you're still interested in physics then, maybe not. But magnets have these invisible lines. You can't feel them. You can't stick your hand next to a magnet and go, I can definitely feel the pull because you're not magnetic. So there's some sort of invisible thing going on. Is there actually anything there? Can you sweep it away with a broom? Can you pick it up? Can you touch it? Can you feel it? No. But it has an effect on you if you're in the area. The last set of fundamental forces are the strong and weak nuclear force. The strong force is what holds protons together inside of a nucleus. So if we've got, let's get this one here. So I've got proton, 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 proton. These things are jammed in the nucleus. And there's probably, I think there's not electrons. What are the other electrons? Neutrons. There's some neutrons in there. And they're all jammed in there. But we know that opposites attract, and kind of conversely, like things repel. So we also have some, let me draw some dots here. We've got some electrons whizzing around. So if we follow the old adage, opposites attract, similar things repel. These are a whole bunch of positively charged protons in the middle, and these are a whole bunch of negatively charged electrons. So we would think that these positives would pull the negatives into them, but that actually doesn't happen. The electrons don't get pulled into the nucleus. There's a reason there's a nucleus and then like a cloud of electrons floating around it. It's because of the strong and weak nuclear force. Likewise, these positive protons don't like being near each other. They're like a whole bunch of really strong-willed individuals, and they don't like being together because then they don't get to be the loudest person in the room. So they push each other out, and that this force that holds them together, the force that counteracts this electromagnetic force of the charges, is the strong nuclear force. Because they're so close together, there's this other force that only really works on the size of like a nucleus, and it holds these things together. The weak nuclear force is kind of involved with particle decay. To be perfectly frank with you, I never took that class in college because I was a teaching major. I learned to be a teacher, not to be a physicist. So they said, you know what, teachers don't need to know about that. So they never let me take the class. There wasn't enough room in my schedule. So I looked it up, but the weak nuclear force is essentially how like nuclear fission and fusion works, like how stars turn hydrogen into helium. That's the weak nuclear force. The strong nuclear force binds nuclei together. Cool. Okay, so all of these things act invisibly and at a distance. When we draw force diagrams, I tell you guys, you can't put a force on something if something isn't touching it to push it or pull it, except gravity. So all four of these fundamental forces are invisible and work on one object to another without any contact. So they're all invisible and they work through these invisible field lines. We draw these invisible lines to show how these things interact with each other at a distance because they're not touching. And that's kind of what vector fields are. Okay. Now let's get into some math, and then let's talk about some nuance that you need to know about that I don't necessarily think is the end of the world, but the AP test told me I have to tell you about it. So here is the universal law of gravity, meaning here's how gravity works on big things. We have talked about how the force of gravity on Earth, if I want to know, here's the Earth, here's me standing on it. If I want to know my weight, we know that this is just mass times little g, or the acceleration due to gravity. But if I'm really, really far away from the Earth, I'm floating out here in space, gravity is not going to pull on me as strongly because I'm farther away, right? Our Earth doesn't get pulled on by stars in another galaxy. Well, it does a tiny bit, but not nearly as much as, say, our own sun pulls on it. So this is because gravity, there's a universal law for it, and this is the equation. This equation is only good if you are standing on the surface of a planet, and it's an approximation. This this one applies to everything in the whole universe, no matter how close it is or how far it is. We don't have to worry about our little g changing because I went too far away. We don't have to worry about changing gravitational strength. This equation tells us how it changes, and we can actually get this equation down here from this one. And we'll probably go over that in the next video. Okay. So the equation, the universal law of gravity, the way the AP test presents it to you is the absolute value of the force of gravity is equal to capital G. This is the gravitational constant. Think about it like little g, but for big stuff. It's a constant that we put in our formula just to make the numbers and the units work out. Okay. So a constant, it's this. We'll talk about the units of this on the next slide, times the mass of the first object. So if I've got two objects here, here's a star and another star, and they're curving space-time, we'll say this one, the bigger one, is capital M, and this little one is lowercase m. So it's the mass of one object times the mass of the other object that are being attracted, divided by r squared. And r is the distance from the center of one to the center of the other. Okay. So g times m over the distance between them squared. And then this will tell us how much force these two stars are applying on each other. This cool grid thing, I hope this looks nice. Hopefully you guys compliment it and you don't go, oh, that's ugly, Mr. Barton. You're a terrible artist. But this is kind of how Einstein described gravity. He explained that space and time are like one thing, a four-dimensional space that we live in, and mass curves the fabric of that space. This is a two-dimensional representation because it's kind of hard to imagine four dimensions when we're only three-dimensional things. But you get what I mean. So the mass is curving these vector fields, and the deeper the curve, if you put like a really big mass in there, let me see if I can get a big mass. Got a big mass, right? Then our vector field would be curved a lot more, like this. And it would pull way harder because it's curving space more, and they're kind of falling into space on each other, which is an interesting way to think about it, I think. So anyway, this is the universal law of gravity. We're not going to do an example problem with this because they're just brain dead easy. It's like this planet has this mass. This planet has this mass. They're this far apart. How strong is gravity on them? Or something to that effect. What we will do is find the units of this capital G, because it's good to practice our unit analysis every once in a while. We haven't done it in a while, so maybe let's bring it back up so that we're not kind of rusty for the AP test. So let's start by taking a gander at the equation. So the force of gravity, big G, little g, whatever floats your boat, equals G m over r squared. What we're going to do is we're going to replace each variable with the units that we measure that variable in, and we're going to try and guess the units for capital G. So force we know is measured in newtons. All right. G, we'll just leave it as G. It's a variable. We don't know it yet. Mass is measured in kilograms. Mass is still measured in kilograms. And distance between them is measured in meters. And because it's squared, we'll have meters squared. Okay. Let's see if we can make this. Let's clean this up a little bit. We have G times kilograms squared over meters squared. Okay. And then newtons, remember, is kind of shorthand for a more complex unit. A force is a mass times an acceleration. Whoops, mass times acceleration up there. And the units for mass are kilograms. The units for acceleration are meters over seconds squared. Okay, so we've got kilograms, meters per second squared. Let's try and solve for g now. So we could divide kilograms squared on both sides to get this to go over there. So we're going to divide by kilograms squared, divide by kilograms squared. So these kilograms cancel these kilograms. Now we got to get rid of this divide by meters squared. So we'll multiply both sides by meters squared. Times meters squared. So these cancel. And what we get is that G has units of this kilogram cancels one of these. Meters times meters squared, we can make this meters cubed. So meters cubed over kilograms seconds squared. And that's the unit for G. Meters cubed per kilogram seconds squared. Don't try and make sense of this. This is one of those cases where physicists measured stuff. They looked at the masses of objects. They looked at the distance between objects, and they measured the force, and they said, okay, but it's not 1-to-1, right? Because if I measure stuff in kilograms, whoever made the universe probably doesn't measure stuff in the same kilogram that I did, right? So we need a constant to kind of scale it to make it work out right. And to turn the things that gravity seems to depend on into a force. So they just slapped this G on the front of it, which is this number, 6.67430. Is that correct? Yeah. Times 10 to the negative 11th meters cubed per kilograms seconds squared. This is the ugliest thing I've ever seen in my whole life. But we need it so that when we plug in our numbers in SI units, we get a force in newtons back out. If we didn't have this, our units would be all messed up, and it's kind of like a formality. It's like a cleaning up thing. It's, I don't know what it's like. I'm not gonna make a metaphor for it. It's a constant that we need to make stuff work out. Okay. So there's G. Enjoy. What a fun activity. Okay. Let's compare this. We're kind of looking ahead a little bit here. We're going to compare the force of gravity to the electromagnetic force. So here is our universal law of gravitation, our constant that's super ugly, times the mass of one object times the mass of another object times the distance between them squared. Our force for electricity and magnetism. This is the force between two charged particles like a proton and an electron. So the force between a proton and electron is K. This is not the spring constant K. This is Coulomb's constant. It's very, very similar to capital G. It's a constant that's there to make the numbers and math work out nicely. Okay. Times Q, and Q is for charge. Wait, hang on, not charge. Charge. Don't ask me why charge is Q. You know what I mean? It's like quarge. Charge? I don't know. Maybe old people couldn't speak good English. But Q is the charge, meaning like this has a positive charge and electrons have a negative charge. It's the charge of them. How charged up are they? Divided by the distance squared. So it's some property of the object times that same property of the other object divided by the distance between them squared, r. That's the same thing we have here. We have a constant a property of this object times the same type of property for this object divided by the distance between them squared. This formula, this general formula of constant property over distance squared, this is known as the inverse square law. It's like that meme that's kind of going around, right? I don't know if you've seen it. It goes something to the effect of if I had a nickel for every time a fundamental force of the universe was divided by r squared, I'd have 2 nickels. But it's weird that it happened twice. You know what I mean? It's not a lot of money, but it's weird that it happened twice. So this is kind of a thing that the AP test wants you to be aware of. These are called inverse square laws. They're very important. They're fundamental. What you're going to do with them is, I don't know. They want me to tell you that they exist. That's kind of what this lesson is me telling you a bunch of stuff exists. There's not a lot of doing with this knowledge of existence. I'll make you calculate some forces, but your homework's not going to be super crazy. It'll be more like vocabulary homework than it will be doing homework. So, okay. So let me perhaps confuse you, I guess. My goal here is to confuse you and then show you that there's no reason to be confused because it's like needless semantics. But let me maybe show you an analogy we can make here. If we're talking about our electrical force, how strongly charged particles attract and repel each other, we've got our proton, we've got our electron, and we've got their charge, meaning their electrical charge. And this is just an innate property of protons and electrons. Okay. Are you comfortable with the idea of thinking of mass? Mass is the charge. It's so hard to spell wrong. Of gravity. Are you okay with that idea? Mass is the charge of gravity. And mass, negative charges for mass don't exist as far as we know. There's no such thing as anti-gravity. There's no anti-mass. Well, there's anti-matter, right? There's anti-protons, anti-electrons. But there's no anti-mass. There's no mass that pushes it away. Mass and gravity only pull. They don't push. Which is maybe good for us. What if we were pushed away from our sun? That'd be crappy. So mass is the charge of gravity. How's that idea sit with you? Okay. Let's go talk about some nuance that I don't think is totally necessary, but they want us to talk about it, and then I'll tell you why you care for your AP test. Okay. There is this idea of an inertial mass and a gravitational mass. And this is purely semantics, meaning this is just people being needlessly nitpicky. Maybe it's not needlessly nitpicky, but it's nitpicking as far as you're concerned in high school, right? So inertial mass is the mass, wrong color, sorry, that determines the proportionality between an applied force and the acceleration of an object that the force is applied to. So let me try and elaborate on this idea a little bit. Inertial mass is the mass that makes something hard to get moving. It's the mass from force equals mass times acceleration. The bigger my force, or rather the bigger my mass, if we rearrange this the way Newton postulated it, acceleration equals force divided by mass. The bigger my mass, the smaller the acceleration I'm going to get from a force. This inertial mass is resistance, stance, sorry, spelling, to motion. That's what inertial mass is. Because I'm heavy and I have a lot of stuff in me, I'm hard to move. That's inertial mass. Okay. Gravitational mass is the mass that determines the strength a gravitational field pulls on a massive body with. This mass is weight equals mass times gravity, or the force of gravity equals g mass times mass over distance squared. This gravitational mass is the charge of gravity mass. This is what determines how hard gravity pulls on you. And if right now you're thinking, yeah, they're the same thing, what about it? Let me maybe give you an example that is weird to you to show you why this is weird. Okay. We'll ignore this sentence for a second. What if protons actually let's back up. Let's think a little bigger scale than protons, shall we? Okay. Let's think about like static charge, right? What if you had a sock? Here's your sock. Okay. What if you rub your sock on the carpet and it gains a whole bunch of charged particles? I don't know if they're electrons or protons. Let's pretend they're electrons, right? Let's pretend you get a whole bunch of negative charged particles on your sock. What if, because your sock was charged up, it were harder to push? Your sock felt noticeably heavier because there was static on it. What if, instead of the force of gravity being dependent on mass, what if the force of gravity was dependent on the charge of something? Or actually, I think I have this a tiny bit backwards. What if, let's back up. Let's back up a tiny bit. I apologize. What if the force of gravity depended on mass, right? There's X number of carbons and stuff in here. I weigh it. The mass is whatever. Okay. It weighs the same amount. I get static on my sock. It weighs the same amount. But the inertial mass was F equals Q times A. So things weren't hard to move because they weighed a lot. Things were hard to move because they were charged up. What if? Isn't that a bizarre idea? If your sock had static on it, it'd be too heavy for you to pick up. And you'd have to like go zap your dog with it before it was light enough for you to pick up. What if the resistance to moving were because of charges and not because of the number of particles in something? That seems weird, right? That's kind of what they want you to be thinking about, the difference between inertial mass and gravitational mass. Is it weird that things are harder to move because there's more stuff in them? That's the difference, okay? So, lucky for us, the charge of gravity, the gravitational mass, the Fg equals g m over r squared. These m's are the same m as F equals ma, because that's just the way the universe is. There's not a lot of because in physics, because that's the way it is, and that's what we've measured. So let's read this last sentence. These two things are experimentally indistinguishable from each other. So no matter how I measure mass, and we'll talk about ways to measure in a second, no matter how I measure the mass, the charge of gravity is always numerically exactly the same as something's resistance to motion. They're experimentally indistinguishable from one another, and they're always the same value. So here's another meme, if you will. Have you guys seen Incredibles 2, where Dash asks his dad to help him with math, and he gets all frustrated, and Dash is like, "Dad, you're doing your math wrong." And his dad gets mad, and he goes, "How can math be wrong? Math is math," right? For us, mass is mass. There is no difference between gravitational mass and inertial mass as far as scientists can tell. But it's some nuance that's interesting to think about, if nothing else. So let's talk about not why you care. I assume you care a whole bunch about this. Obviously, you're going to go home and tell your parents and say, "Mom, Dad, did you know there's a difference between inertial mass and gravitational mass?" And they're going to tell you to shut up and mop, right? But let's talk about why you care. And it's because it's on the AP test, potentially. If the AP test asks you to come up with an experiment to measure the inertial mass of something, that experiment has to be different than the way you measure gravitational mass. So let's talk about how you can tell which one you're measuring. To measure inertial mass, you would apply a known net force to an object. So you push on it, or pull on it if you want, then measure the acceleration. Then we use Newton's law, F equals ma, sigma F. Whoops. Oh, darn. Oh well, it'll be ugly. That's fine. We apply a known net force, we measure the acceleration, and then we find this mass. The known net force, though, cannot be gravity. Because if you're using gravity to find the mass, you're finding the gravitational mass. So we'll talk about what are some other ways that we could set up a known net force to try and calculate the inertial mass of something. Likewise, if we want to know the gravitational mass, we do pretty much the same thing. Is we need to measure the force on the object because of gravity and then divide by the acceleration of gravity. We're not going to worry about how you know this number, but we're going to use the idea that the force of gravity equals mass times g. And then we're going to use the force of gravity to find the mass. If you use gravity to find the mass, you're finding the gravitational mass. If you are forcing yourself to find the mass without gravity being involved at all, you're finding the inertial mass. So let's go ahead and talk about two ways that we could find the mass, the inertial and the gravitational. Okay. Let's start with the inertial mass. To find the inertial mass, we can't use gravity. So the obvious thing of get a scale and then hang the mass, that's an ugly hook, hang the mass from the scale and then read the force. This isn't going to work because the thing pulling the mass down and weighing down this scale is weight. So that's bad. We're not allowed to do that. Okay. Luckily, we've done another experiment in this class where we've found some acceleration and then looked at some masses, right? One way we could find the inertial mass is we get a cart with very low friction wheels. Okay? Very low friction. The reason we're trying to ignore friction here is because usually friction always is mu n. But usually n is counteracting our weight. So if n is somehow related to the weight, you're secretly hiding gravity in there, which is not good. Okay, so we can't use the normal force either, unless we can find a way to make it not have to do with gravity. Okay. So we get our frictionless cart and we put our beautiful mass on top of it. And then we could do a couple of things. We could put a force gauge on this. So we like hook it on here. Force gauge. It could either be a scale or it could be like a digital one. And then we pull this thing so that this stays constant. That way we're applying a constant net force. And then on the other side, oops, my cart and stuff fell apart. And then we pull it maybe away from, say, like a motion detector, right? And then we use our motion detector, find acceleration. And the way we could do that is maybe look at a velocity versus time graph. Look at the slope. Slope is acceleration. Now we know the net force. We know the acceleration. And then we can do F equals ma and then solve for mass that way. This way, we're not including gravity at all. Make sense? Okay. There are other ways we could do this, but this is one good way that we could do it. All right. Gravitational mass is easier, which is why I saved it for last. We'll just do it the way we couldn't do it before. We get our scale, and then we hook our mass on here. And then we figure out what is the force in newtons that this scale is reading. It'll say 10 newtons. Okay. And then if our mass is stationary and not moving, then we have two forces counteracting each other. We have the force of the scale, which equals the force of gravity, or the weight. So this is telling us our weight. Then we just say weight equals mass times g. We divide by g as best that we know it, and we could measure that some other way, hopefully. And then we just do the force, the weight divided by g, and that'll tell us our gravitational mass. Okay. So hopefully this lesson wasn't too crazy. I think it's got a lot of interesting stuff in it, and maybe you'll like it because you don't have to do any math, right? But if you have questions, let me know. If you're confused about the nuance, let me know. If it's not too much trouble, like and subscribe. All right, I'll see you next time. Have a great day, you guys.